So this is kind of one of those things that I think is really awesome. So if you think back towards any of those crazy science shows you get to watch over on CSI or something like that, they always find this crazy white powder. Like, what is it? Well, this is how we find out what is it. You know, how do you tell that one fluffy white thing? Did you get the reaction to work? Did you get the reaction not to work? Did you create the next Nobel Prize with this cool thing that happened? How do you know? Is to go through and look at spectroscopy. So we got some time to chat today, and so what I'm going to like to talk to you all about is a bit about looking at spectra. So what kinds of things do we expect to see? We're looking at, right now in 118A, we're looking at IR, we're looking at proton NMR. So what kinds of information can we get? Where are the ranges? Where's the general patterns? And finding information in those spectra. Because it's, yeah, I can tell you, no table 11.4, that's your IR table. Those are numbers you really kind of want to know. No table 10.2, and go hard and short, that's your proton spectra numbers. Those are your general patterns and things you kind of really want to know. But within that, there's a bunch of patterns that make it easier to remember. So we can sit down and talk a little bit about, well, if I don't know exactly where this is, it's over here, it should be something like this. Well, going back to those first principles. Going back to, where is our electron withdrawing? So look a bit at that, and then look at how do we put this together? How do we do a problem? I mean, what do we have? What kind of information can we get? What kinds of approaches can you do? And I'm going to walk you through my favorite approach to doing these, which is by far and away not the only approach. So, at least for my section, I talked to the TAs and I said, don't teach them my way, teach them your way, so that they see my way, they see your way, they see everybody's way, because you guys don't think differently. So where it works for you to think is where it works for you to think. So take what I'm doing here. I like to think it works pretty well, because I've been doing it for a really long time, and I've been refining it for a really long time. But if it doesn't work for your brain, think about talk to your TAs. Say, how do you do it? How do I get this organized? But a lot of approaches to spectroscopy, you really just need to be logical. You need to sit down and be organized with that information and come up with a process that allows you to treat this like a logic problem. Unlike most everything else we do in the 118 series, there's not a lot of actual chemistry in this. The chemistry is mostly looking at the spectrum, knowing why one signal is where it is. But most of the actual stuff of doing these is doing logic problems. If you like doing Sudoku, you'll eventually like doing spectroscopy, because they're the same sorts of thought patterns. How do you get these pieces to go together? If you don't like them, well, sorry, that's one of those things we occasionally have to do. How do we? So when we've got a spectrum, when we've got a spectroscopy problem, we usually have three sorts of things. We usually have a formula. If you don't have a formula, this gets about a dozen times harder. So anytime you're going to see one of these in class, you're probably going to have a formula. And with that formula, we're also generally going to have an IR or some IR information, infrared, and proton NMR, HNMR. So we spent the last couple of weeks in discussion talking about all these things and talking about kind of the general patterns. So I'm not going to spend tons of time on it, but I want you to get a couple of patterns, just sort of quick reminders and little helps on figuring out where those numbers are. What does the formula give us? This gives us our degrees of unsaturation. Also, some people call it double bond equivalence. That's your 2 times your number of carbons plus 2, minus the number of hydrogens, plus the number of nitrogens, minus halogens, all over 2. One of those formulas you kind of want to know. Other people calculate it slightly different ways. If your TA gave you a different version, it's okay. There's a couple of different types of calculations for that. But that's the one that I tend to use, and what that's going to help us with is see how many double bonds you have, how many pi bonds, and how many rings. And this is one of those things when we get to kind of doing our process, it's usually the first thing I do. Because if you have an alkane ring in there, there's no other way to find it. You got a cyclohexane, cyclopentane in there. They show up as normal alkanes, and looking for that degree of unsaturation is the only way you can say, ah, that's it, that's the piece I'm missing. IR, we're looking at the bonds and kinds of bonds. Proton NMR, we've got a lot of different information. So for the IR, really, when you're thinking about those signals, there's 4 places you want to look. So you can kind of roughly divide this into 4 sections. They're not even sections, but we're looking at about 2,700 and higher, 2,700 to about 4,000 on that left-hand side. And that's your something attached to hydrogen zone. So doesn't matter what that something is, it's something attached to hydrogen. If it's way up there on that left-hand side, you're looking at something attached to hydrogen. And within that, we see a couple of neat shapes, a couple of neat functional groups. You can see your OHs, you can see terminal alkyne Hs, you can see all sorts of fun patterns. Big things for that range, we'll just call it kind of zone 1 over here, so I can kind of make some notes. Stuff for zone 1 is right around 2950 is regular old alkanes. So if you're looking for that reference point, you're looking for that big sort of blurry, jaggedy shaped peak that says this is my regular old alkane stuff. There's usually a little bit of a blur to it, a little bit, a couple of signals there, because what we're doing is saying there's a lot of different CHs. But what that can provide you with is a reference point. If it's over on this side, if it's on the right side, it's lower than that number-wise, you're looking at an aldehyde. You're looking at something that's a particular type of bond. If it's on the other side, you're looking at an alkene, or even an alkyne, even further down. So if you don't necessarily remember your numbers exactly, you can still get a sort of general idea of what's going on. If you do remember your numbers, aldehyde's usually around 2750. Alkenes around 3100, and that alkyne's around 3300. And that's a nice sharp those are all nice sharp peaks. They're all nice spiky things. So shape in IR does have some information as well. We can look at that and say, I don't necessarily know what my peaks are, but I may recognize the shape of them. Okay.
So you're saying that shape, how it's shaped, can tell you any of the...
So the shape is, really the shapes for all of these are going to be about the same. They're all going to be little spiky bits as opposed to broad bits. So we'll get to some shapes here in a second. But what we're looking at is if you can find in your IR, if you're looking at that basic IR spectrum, you're going to see something that's got a little bit of a jarry bit, and then later on we're going to find our fingerprint region. And that's a good reference point. Say, where's my fingerprint region, where's that alkane? Because it's in pretty much every molecule. So we're looking just to the left of it or just to the right of it, we're looking at certain types of groups, even if you don't necessarily remember exactly what the number is. Because that's almost all molecules that are organic have alkanes in them. I mean, there's exceptions, but most everything's got some CHs in there. How we do? So, the other fun thing over in this zone is we get OHs and NHs. And OHs and NHs can be a little hard to tell apart from each other, especially in the first while you're practicing these. But they tend to have very similar chemical, or very similar wave numbers to that alkyne, but they've got a very different shape. They tend to be broad. They tend to be right around 3,300 again, which makes them a little bit funny to find. There's a couple of things there, but they've got this really broad shape. We're going to see this with OHs and NHs throughout spectroscopy, because if you think back to those first principles, you think back to Chem 2A and Chem 2B, we're looking at intermolecular forces, we're talking about hydrogen bonds. So hydrogen bonds, OH and NH are really interested in their hydrogen bonds. They spend all their time hanging out with that hydrogen bond, talking to that particular type of interaction, and they're completely ignoring the rest of the molecule. So they've got lots of little bits and pieces, but they're broad, and we're talking about how much hydrogen bonding do we have, without really necessarily spending a lot of time talking to the rest of the molecule. So they get that big, broad shape, which is nice and distinctive. So if you're looking at something, you're seeing that broad shape, it's probably an OH or an NH, either an IR or an. How we do? So next zone, we're looking at right around 2,200 or so, down to, so we can say 27 to 1,800 or 27 to 1,900, but really it's a much narrower range. It's your triple bond region. So that's zone 2. And there's not much in it. There's alkynes, carbon-carbon triple bonds, there's nitriles, carbon-nitrogen triple bonds. That's it. That's what you got. So if you see something there, you know you've got a triple bond. If you don't see anything there, you know you don't have a triple bond. And otherwise, if we're looking at that sort of basic spectrum, there's this big gap. So if there's nothing in there, there's nothing in there. It's just all the boring old alkanes. Go a little lower, zone 4, double bonds. Carbon-carbon, carbon-oxygen. You can get carbon-nitrogen bonds. They don't tend to show up till 118C, but they exist. So that's your double bond region. Look at 1900 to about 1500. And below that, zone 4, we're looking at single bonds. Most people call this the fingerprint region. It's really hard to interpret. I can't do it. I've been doing this a long time. I don't bother. There's not a lot of information in there. It's really complicated. So you can take a look at that and say, hey, I know I've got alkanes. You can say I can match it to a molecule if I know what's going on. But it's not going to tell you a lot about what the molecule is. If we don't know what it is and we don't have a match for it, we're kind of out of luck. But within that, we can say, well, I still can see this is my regular old fingerprint region. Here's my zone 2, here's my zone 3, here's my zone 2. We can get that reference point. And kind of a last little fun thing with those alkynes, alkenes, and alkanes in IR is you can see a pattern here. Weaker, longer bonds on the right, shorter, stronger bonds on the left. So short and strong. Weak and long. And that's true in all of those zones. The shorter and the stronger the bond is, depending on what kind of weird functional group you have, the more it's going to go to the left. The weaker and longer that group is, depending on its functional group, the more it's going to move over. So you see these patterns for all sorts of things, and they come up in other functional groups as well. How are you doing? Questions on IRE stuff? Yeah.
How do you know you have a ring?
So you don't know you have a ring unless from an IR. There's no good way to tell in an IR whether you've got a ring or not. So IR just tells us what kinds of bonds do we have. It doesn't tell us necessarily how they're oriented or how they're put together. So ring is really, it's part of the fingerprint. And if you're really good at fingerprint, you may be able to tell if you've got a relatively symmetrical molecule that it's a ring or not a ring. I'm not that good. So, it's going to be really hard to say what's going on in there. Where we're going to get most of that ring is that degrees of unsaturation.
If you know it's a ring, you have there's a degree of unsaturation, but there's no mark in the...
Yeah, so if we have a degree of unsaturation, and we don't have a ketone or an aldehyde, and we don't have a C double bond O, and we don't have a C double bond C, and we don't have any C double bond C hydrogens, and we don't have any triple bonds, we don't have any of this, it's got to be a ring. So you can do process of elimination. And that's also a really good point with a lot of this spectroscopy, is sometimes lack of information is just as useful as actual information. There is no signal. That means there's nothing there. Can you read hybridization of? So to a certain extent, yeah, you can think about hybridization, because anything that's sp is going to be having those triple bonds. There's actually true sp stuff, carbon dioxide tends to show up in there. Stuff that has sp hybridization tends to show up in that range too. It's a little off. But we do tend to see, within the basic functional groups we see, we do see those hybridization patterns in there too.
In an OH triple bond and a double bond,
Mm-hmm.
how would they affect the OH?
So triple bonds with the OH, we can usually kind of see that little spiky bit, because if we have not a terribly strong absorption, we can see that. It's hard sometimes to see double bonds or benzenes because they tend to be on this side and you can't really tell if it's a bond or just a jagged bit on the edge somehow. So those double bonds can often get lost in that OH, just blurs them out. But the alkynes are usually pretty close to the bottom, so you can usually see them again. But if you have alkyne hydrogens or alkene hydrogens, that's when we go to the proton. We go to the proton NMR and we get a lot more of this information. So we're not really ever going to solve the molecule with just the IR.
You have that little dip in the OH or the triple bond, that's true.
Yeah, so if you've got an alkyne, you could see just the CC, or you could see the CC and the CH. And that'll give you know, you'll know if it's inside or if it's got that H attached. And then you can go to the NMR and take a look at that too. Okay. So, similar patterns for the proton NMR. I'm not going to give you every single chemical shift there is. There's not really much point to me to just waste your time doing that. We've got more interesting things to talk about. But within that region, there's a couple of general patterns that can make knowing those numbers a little bit easier. So table 10.4, know your numbers, know your numbers, know your numbers. That's your proton NMR, full heart and shoulder. Table 11.2, that's your IR. Know those numbers. We're going to be refining them as we go through 118B and 118C. But what we have right now for proton NMR is really a scale that goes from 0 to 10. And the thing that they never really tell you, but it's kind of, if you spend your time staring at spectra for a while, start to notice, is everything that's on the right half of that, or most everything, it tends to be sp3 hybridized. Pretty much everything that's on the left side of that 5, left half of that spectrum, tends to be sp2 hybridized. I mean, sure, there's a couple of exceptions. You can get things that have 2 electronegative groups at 5.1, and they're still sp3. You can get alkenes at 4.8, and they're still sp2. If you kind of take a rough estimate, you can really see mostly sp3 to the right, mostly sp2 to the left. Upfield for sp3, downfield for sp2. And within that, we start to see a couple of zones. 0 to about 1.7. These numbers are going to vary depending on who you're talking to and how broad their ranges are and what their classifications are. Or just alkanes. Regular old boring CH. Totally shielded. Nothing interesting is going on here. Nothing fancy. Got our CHs. We start to get a little bit of electron throwing. Remember that when we're looking at that spectrum, what we're looking at is how many electrons are around the nucleus. Lots of electrons to go to the right side. So, lots of electrons over there on that shielded side. Lots of partial positive on the left side. We've got a lot of D shield, we've got a lot of electron withdrawing groups. So, even if you don't remember your exact numbers, you can start thinking about what's going on with the general. What is going on with my structure? Do I have really nothing pulling electrons away? It's going to be really shielded. It's going to be alkane. Do I start to get something a little electron withdrawing? 1.7 to 2.5, 2 to 2.5. I call this the alpha to something interesting range. Alpha meaning it's next door. It's not actually attached to that weird functional group. But we don't really necessarily know what it is. So that alpha to something interesting range is something that's next to a pi bond. So we've got some sort of pi bond, and we're looking at the hydrogens not on the same carbon, but the ones next door. They're sp3 hybridized, they're not part of that pi system themselves, but that pi system is pulling on them just a little bit. Just a little electron withdrawing, just a little bit of sp2, just a little bit more s character pulling those electrons to the nucleus. And so we just get this little tiny chunk. Not a lot. And if you're really good at this and you spend a lot of time memorizing very subtle numbers, you can tell the difference between these two groups. But at this level, it's a little awkward. But what we find in there is stuff next to pi bonds. Stuff next to benzene, next to alkenes, next to alkynes, next to ketones, next to aldehydes. Alkynes themselves are in that region. There's a dozen different kinds of functional groups next to esters, next to acids, next to amides, next to anything with a pi bond tends to show up in there. So it can be a little hard to tell exactly what it is, but at the same time it can be, well, I know it's next to something interesting. It's not just plain old boring alkane, and that can be a pretty good clue. We go from about 2.5 to 5, and this is CH, some sort of heteroatom. The more electronegative that heteroatom is, the more to the left. Oxygen tends to hang out near 4, nitrogen's closer to 3, halogens are somewhere in the middle. Chlorine's more nearby oxygen, bromine's more near nitrogen, iodine's actually kind of up in that 2 to 2.5 range again. So we're looking at just sort of how electronegative is it. And It may be a little hard to tell, sometimes those ranges overlap, so even if you know your numbers really well, you may be not sure. But what you can do is still think about, what's in my formula? Can't be a nitrogen if there's no nitrogens. Can't be a chlorine if there's no chlorine. So think about what's in your formula, think about what's in your options, and you can start seeing, well, what kinds of things are really electronegative. Now, the reason why I like to think about this way is it all comes down again to the exact same thing on the other side. 4.8 to about 6. We're looking at just boring old alkenes. Nothing terribly interesting. There's sp2, that's the cool part. There's something in there that's got something going on. But they're just C's and H's. There's no real electron withdrawing group. There's nothing really pulling on those electrons besides the fact that they're pi bonds. You go a little lower. Generally between 7 and 8 is the major region, but it can go anywhere from 6 to 9. We're looking at aromatics. And it's not entirely true why these are exactly the same as those alpha to something interesting, but they are analogous. They're saying, well, we've got a pi bond, and it's next to a pi bond, and it's a little bit more de-shielded. There's more fancy stuff going on in there that we'll talk about in 118b, but really, it's a pi bond next to a pi bond. It's a little more de-shielded than a plain old boring alkene. So we get that same pattern again. You start trying to add in really electronegative atoms, there's your aldehydes, way down there at 9.5, 10. Really, really de-shielded because we're not only sp2, we're also got that really electronegative atom. Oxygen calling on those electrons, stealing them all away from carbon. Carbon's got a giant partial positive charge. And again, we're saying really what we're doing, sp3 getting more and more and more and more de-shielded, more and more and more partial positive. Switch to sp2, pretty formal, more and more and more and more electron withdrawing, more and more partial positive. How we do? Question?
Where does alcohol fit in?
So alcohol, good question. So alcohols and amines, or really any OH and NH, they get kind of funny. Because like I was saying with the IR, they're broad. They get a different peak shape. We'll talk here about peak shape when we actually start looking at spectra. But they're kind of this broad in shape. They've got that blurring because they've got all that hydrogen bonding. So they're really focused on that hydrogen bond, which means they don't really show up very cleanly in those spectra, which means they can be a lot of different places. So this is the other reason I like to use that sp3, sp2 kind of dividing line, is because OHs and NHs that are just plain alcohols and just plain amines, and there's not sort of fancy double bond stuff going on, show up somewhere in the sp3 region. OH and NH show up alcohols and amines, same range, 0.5 to 5 is the end. It's a huge range, and it really depends on concentration more than it depends on function. How much hydrogen bonding we get. But when we'll see this not so much in 118a, but kind of just keep it in the back of your brains for the next couple of quarters, when we start getting stuff that's got pi bonds, we start getting stuff attached to benzene, attached to an amide, attached to next to a pi bond of some sort, and we turn that into an sp2, amides tend to show up between 6 and 8 ppm. Carboxylic acids tend to show up way downfield. So things that are sp2 tend to show up in the sp2 region. So they tend to vary a lot still because of that hydrogen bonding, but they do tend to show up in the sp2 region as opposed to the sp3 region. So it kind of helps keep track of what's going on with them. Because those guys are squirrely, they just run around. You can't necessarily tell where they're going to be today. How do you do?
Something next to a next to a pi bond. So it's a C with the H, like what's the next?
So if we're looking at that next to a pi bond, what we're saying is we've got an sp3 hybridized regular old CH. It's not a pi bond itself. There's no pi bond attached to that carbon at all. But the next door neighbor, if you think about each carbon in that chain as a house on a street, and we're talking about those hydrogens as living at that house, This house doesn't have a pi bond in its backyard, but his neighbor does. So they can go over there and have, think about it like a pool. It's got this pi bond in there. And we can go over and kind of spend a little time there, but we have to ask permission and knock and say all these nice things about them, use that pool, use that pi bond. So there is some influence, but it's not ours. So it's not actually on that pi bond, it's next door. How we do? Technical term for this is alpha. We often say that the carbon where the fancy functional group, wherever it is the ipso carbon. That's the one with the cool thing on it. Could be a haloalkane, could be a ketone, could be a benzene, could be all sorts of things. But the one next to that is alpha. The one next to that is beta. The one next to that is gamma, and then we get lazy and stop counting. Really, there's no influence any further than that. We really can only shout over so many houses. But yeah, you will see a lot of alpha influence. And you'll see it all throughout county, so it's not just spectroscopy. Everything we learn in here goes back to everything we learned about reactions. Everything we learned about reactions comes back to what we're doing with this. It's all the same principles. How we do? Let's do a problem. Let's actually get some of this stuff engaged and going into something. So I'm going to pull my samples here for those of you guys who have it off of my kind of practice problems up on the my course website. If you don't have it, Alicia said she was going to post it over on the Learning Skills website, so you can take a look at that. And if you're just listening to the podcast because you didn't get to come here, well, you should be able to get that off the website somewhere. So we're going to start out with just compound A, because it's got some cool tricks in it. And I'm going to kind of write this up over here so we can all follow along. And then scribble all over it, so that's what we do. So, while I'm scribbling and talking at the same time. Trick with dealing with spectroscopy. We've got a formula, C11, H18, O2. We've got an NMR spectrum. That NMR spectrum is running from about 0 down to about 4. We don't have anything lower than that. That's okay. So if your spectrum cuts off at 4, it's because there's nothing interesting down below that. 3, 2, 1. Got a 7. 1, 2, 3, 4, 5, 6, 7 peaks. 1H, way down by 4. Cluster of stuff up by 2.5 to 2. Triplet, triplet, singlet, 2H, 2H. 3H, some fancy pentets, 5, 5, each of these are 2H, and right around 1, big 6H jump. So that's our proton spectrum. If we look at the IR, starting around 4,000, zigzag, nothing much interesting. We see peaks starting. There's our alkanes, right around 3,000. Nothing much, nothing much, nothing much. Big jump, just above 2,000. Another long peak, and then we just start to get into some wiggles. And we're looking at now 1,500 or so. There's our IR. So, how do we want to go about doing this? What do we want to do? So, the trick with these is you want to sit down and be somewhat logical about it. And I tend to take a very straightforward approach to each individual peak as I'm coming up to it. Some folks like to write tables. Some folks like to just sort of do each peak as sort of shotgun, pick one and go to the next one. I tend to work left to right on my spectrum, because it means I don't lose anything. If you have that, ooh, I like to look at this one because I get it, and I don't get that one, but I get this one kind of approach, it'll work just fine. Just be very, very careful. Because if you don't really pay attention, and mark which peak you've done, and mark which peak you haven't done, and keep track of everything, it's incredibly easy to just do one peak twice, forget to do another one entirely, and now you're just completely confused. Because you got all the wrong bits in it. So whatever you're doing and however you're kind of approaching this, be organized. So, first thing I like to do is double bond equivalence, degrees of unsaturation. In part because, well, if you're on an exam sort of scenario, it's worth a point or two partial credit. It doesn't actually take more than 15 seconds, and that's really it. You know, you can do this. It doesn't take very long, even if you're running cramped on time. Also, if you've got a ring, it may be the only way to know. Remember when we were talking about IR, we couldn't see the cycloalkanes in there. Well, we can't see a cycloalkane in the NMR either. It just looks like alkane. So if we have that ring, the only way we can tell is probably by looking at that degrees of unsaturation, saying we're missing one. Well, it's got to be a ring then. So it's really useful to do. We take our formula here, 2 times the number of carbons, plus 2, that's the maximum number of hydrogens we can possibly get in there, minus 18, that's how many we do have, number of hydrogens. We would have to add 1 for every nitrogen, because we can stick that nitrogen in a bond and we need an extra hydrogen. We don't have any. We can lose 1 for every halogen, they replace a hydrogen. We don't have any of those either. Divide the whole thing by 2, and we end up with 24 minus 18 is 6 over 2, 3 degrees of unsaturation. So somewhere in here we either have 3 double bonds or 3 pi bonds or a ring and 2 pi bonds or 2 rings and 1 pi bond or something's going on. How we do? So, next bit. Now you can do these in different orders. There's nothing sacred about the order here, but I find for a lot of folks, especially in 118A, we have done IR for just that 1 more week. And that makes it a little bit more accessible. There's a little bit less information in it, so it's a little bit less intimidating. And it also lets you get some idea of what sorts of things you're going to look for in that proton NMR. Because proton NMR has a lot more information. So I also suggest taking a look at that IR next and saying, what kinds of things am I looking for? And if we look at this IR, we're coming along, and we don't see anything significant really in that zone 1. We don't see anything that's an OH, we don't see anything really that's an NH, well, we didn't have any nitrogens in the first place, so that's probably not a big thing. But we don't see any pi bonds, we don't see any alkyne hydrogens. What we do see is just regular old CH. So there's our reference point. There's nothing kind of to the left of it, so there's no alkenes or alkynes or OHs. We don't see that spike just to the right, that's an aldehyde. We've just got CH. If we keep going, we kind of break this down into our zones, say, well, there is something in zone 2. If there's something in zone 2, you have a triple bond. It's either an alkyne or an itrile. C's triple bond C, C triple bond N. They can be really hard to tell apart just from your IR. They've got almost identical ranges, but we have no nitrogen. So if it's a CC triple bond or a CN triple bond, can't be a nitrogen, must be an alkyne. So now we can start saying, well, I know somewhere in here, my pieces I'm putting together, we've got an alkyne. We also know it's an internal alkyne. There's no hydrogen attached to that, because if there was a hydrogen attached to that, we'd see it. There's none.
How would that look different if it was C triple bond?
C triple bond to an O?
Yeah.
Well, the only one you're ever going to likely see is carbon monoxide, and it's not very interesting otherwise. So oxygen doesn't like to make triple bonds, so you can get oxonium ions that have carbon triple bond. They're really unstable. We're not likely to take a spectra of them. And you get carbon monoxide, but there's nothing else interesting going on there. So it doesn't tend to show up. It would be probably likely to be in that region though, but it just doesn't tend to be something we see. How are we doing? So we could keep going. We've got this double bond peak. It's more to the left side of that zone on the right. It's probably closer to 1700 than it is to 1600. That's probably a C double bond O. Other clue that it's a C double bond O is we don't have these C double bond C hydrogens. Unlikely to have an alkene without any hydrogens. It's not impossible, but it's not terribly likely. So we probably have some sort of CO. And it's probably not an aldehyde. With an aldehyde, you can see the aldehyde hydrogen. So we've got some sort of CO, ketone, or ester. It's not an acid or it have an OH. It's not an aldehyde or it have a hydrogen. Probably a ketone or an ester. And we keep going in that IR, and we just see fingerprint. There's C's in there. There's probably other oxygen bonds. We've got at least one more oxygen, probably carbon-oxygen single bond somewhere. MIP, fingerprint, don't worry too much about it. It's not easy to interpret. So those are what we got, internal alkyne and a ketone or ester from our IR. Proton NMR. This is really where the meat is. And once you start getting really good at these and have a lot more practice, it's often easiest to just jump right into the proton. It tends to give you the most information. But especially as you're getting started, the IR gives you some clues as to what kinds of things you're going to expect. By the way, we've already found our 3 degrees of unsaturation. We know we probably don't have a ring. If we find a ring somehow in there, something else is going wrong. So proton NMR, I really like to say again, I work it left to right. There's a couple of reasons for that. One, I grew up speaking English, it goes left to right. Two, and more actually chemically, in a real spectrum, very often we don't get this nice, pretty, every peak is nice and separate thing. Very often in a real spectrum, those CH2s that are very similar are right on top of each other. And that makes them really hard to interpret. But stuff that's downfield, stuff that's got electronegative atoms, tends to be a lot more distinct. Chemists are lazy too. We do the easy parts first. So working left to right usually gives you the easy parts first, and anything that's left over, well, I have 3 carbons and 6 hydrogens, they must all be CH2s. You know, we start to kind of figure out from context, even if you can't see it well. So left to right is usually a good bet in a real spectrum anyway. You can do other approaches, but again, be really sure you're organized, do each peak exactly once. What we're looking for here is 3 things. When you're looking for these, you're looking for 3 different pieces of information. And we're looking to say, firstly, chemical shape. Secondly, integration. And thirdly, coupling. Every single peak can have all 3 of those pieces of information. So we want to take a look at it and say, what do we have? What do we know? What's going on here for each and every individual peak? So working left to right, we see first off CH, 1 hydrogen attached, sp3, 4 bonds. It's way down there at like 3.9, 3.8. It's got something really electronegative attached to it. We look at our formula, what we have is oxygen. So we know that we have an oxygen attached to that. We look at our coupling, we have 1, 2, 3, 4, 5, 6, 7 little subpeaks. 7 little subpeaks means that we have n+1 rule, 7 peaks. -1 gives us n must be 6 neighbors. Now, I use this sort of circled number kind of indicator. That's just me. It's not anything absolutely perfect about everybody has to do NMR that way. But what that tells me when I do this is I know there's 6 neighbors, but I don't know who they are. Very tempting to just write down, I know there's 2 CH3s next to it. We've got 6 neighbors, we've got 2 places, they must be 2 CH3s. But if you don't know who those CH3s are, you write them down, then you find them, all of a sudden you write them down again, you got 4 CH3s. Which ones are real, which ones are imaginary, which ones we have to place somewhere, which ones have already been placed. Get confusing again. So I don't write down personally any atoms until I know exactly where they are. I know which peak they are on that spectrum, and then I can write down the atoms. But I do want to write down that information that I know there's 6 hydrogens nearby. How we do? So keep going. Going to go a little quickly here because we're getting a little short on time. I want to get to the good bits. We've got two triplets, CH2, CH2. They're both two H's. They're both triplets, meaning they have two neighbors. And they're both in that alpha to something interesting range, 2 to 2.5. Again, we don't know who's exactly next door, but you can kind of write yourself a little note. I write a little pi bar. Sometimes I write SP2. I know there's somebody next to that that's got a pi bar. Not sure who it is yet, but there's somebody there. Also in that region, CH3, pi bond, 0 neighbors. It's a singlet. One called spiky P. No neighbors on that CH3 means whatever it is doesn't have a CH attached to it, whatever that neighbor is. So lack of information, no coupling. He's actually information since we have no neighbors. So those are our alpha to something interesting, somebody next to pi bonds. We keep going. We've got two CH2 pentets, things that have 5 peaks. They're slightly different. They're not symmetrical. CH2 next to 4. And CH2 next to 4. Also in that region we have 2 symmetrical CH3s. Symmetry is a big clue. We've got 6 H's or 4 H's or 9 H's. You know they're symmetrical. You know they're symmetrical because there's absolutely no way to get that many hydrogens on the same molecule, same carbon all at the same time. So we see, if you ever see that 6H doublet, you know you've got 2 CH3s on the same carbon and there's one neighbor. And that's always, always true. Take a look at the back of the discussion manual. Right at the end of week 9, you see a lot of common coupling patterns. These are good to practice and look at and just sort of get familiar with because they start to come back again. They start to show up and you can start saying, oh, 6H doublet, I know it's an isopropyl group. Done. You know, it doesn't take any longer than that once you start getting used to this. How we do? Now the fun part. So before we get to the fun part, check your atoms. If you don't have the right number of atoms at this point, you're going to completely frustrate yourself trying to get this to put together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. Good, we got everybody. 2 oxygens, 1, 2. Good, we got them. We need 18 hydrogens. 1, 2, 3, 4, 5, 11. Plus 3 is 14, plus 2 is 16, plus 2 is 18. Good. If you did have the wrong number of hydrogens, you did the proton wrong. If you have the wrong number of carbons and oxygens and double bond equivalents, you may have missed something in the IR. If you just have the wrong number of carbons, you may have a quaternary carbon you just can't see somewhere. If you have the wrong number of double bonds, that's when you say, well, I have a ring. Right now, we've got absolutely everything we're supposed to have. No rings, no missing double bond equivalents, got all the right atoms. So this is where this becomes absolutely no chemistry at all, and purely logical. What we've got here is that Jimmy needs to be left-handed, so he needs that chair, and Janie won't sit next to Johnny because they're having a fight right now. Joseph needs to sit by the kitchen because he's cooking dinner, and somebody else, Jenny, wants to go sit by the door because it's hot outside. She wants, where are they all sitting at the table? That's what we've got here. We have all this information. We know it's all true. We've checked all of it with our peaks. We know what's all going on. All we have to do is put it together. So, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Those guys count. They're still in there. They still have the hydrogens attached. So those are all of our pieces. So when you're looking to put this together, I call these candles. There's places you can start to work, places you can start to look at things, and things you want to start. This is kind of the tough part because they're all different. But things to think about is ends versus middles. You can't put 2 ends together. If you put The two CH3s sit next to each other. There's no place else to put the rest of the molecule. You gotta have the ends separate from each other. Think about coupling. Is there a single CH in the molecule? If there's just one CH, who's next to it? It's gonna have a funny coupling. Is there stuff that has CH3 next to it? You have lots of CH2s where you're seeing 2, 4, 2, 4, 2, 4. They're all gonna go together. Look for symmetry. We have a little bit of symmetry in this molecule. We know those two CH3s are exactly the same, so we know that they're going to be exactly the same. Look for electronegative atoms. Who else is next to that oxygen? In fact, that's probably where we're going to start with this one, is who else is next to that oxygen? There's not a lot of good places to put that oxygen where it's not going to show you some sort of weird chemical shift. It needs to be something that has no hydrogens attached. And just sort of general patterns of truth. If you've got a funny functional group, it's probably not right. If you suddenly end up with like 3 oxygens all in a line together, that's probably not it. If it's something that you've never seen anything remotely like this before in lecture, that's probably not it. So think about what sorts of things we're getting, because what sorts of things we're talking about are things that are stable and will actually work. So where can we put these? Where can we put bits together? I said I was going to start with the oxygens, and I lied. I'm actually going to start with that 1H, because it's a little bit more complicated. So we've got this symmetrical group. They're right next to one hydrogen. We need to find somebody, some 1H, we can put them next to. There's only one 1H in that molecule, and that's got to be it. It's the only place we can put that. So we get those two CH3s are next to our CHO. These guys have 1 neighbor, this one has 6. All works out. Coupling-wise, we can also look at, we've got 2 things that are next to 2, and a bunch of things that are next to 4. So 4s are kind of like middles. They need to have 2 things on either side. Sometimes it's 3 and 1, sometimes it's 2 and 2. But if you look at what's going on with your molecule, we don't have any 3 and 1s. So it's got to be things that are 2 and 2. We've got to have things that have 2 neighbors on one side, 2 neighbors on the other. We've got 2 that have 4, those 2 go in the middle. We have 2 that have 2. We put these 2 together. We put these 2 things that are triplets together. There'd be no place to put those things with 4 neighbors. They'd be missing neighbors. They'd be lost. They wouldn't have their friends. So we do need to find a way to get these all to work together. So CH2s with 4 are going to go in the middle. We're going to get CH2, 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 CH2. This is next to a pi bond. This is next to a pi bond. This is our 2 neighbors. This is our 2 neighbors. This one's got 4. This one's got 4. How are we doing? So now because we've finished all of our coupling, we can start talking about chemical shift. We can start talking about where's everybody kind of put together. So chemical shift, or electronegative atoms, we've got some stuff next to pi bonds. If we put them both next to the same pi bond, we'll make a ring and we won't be able to finish off the molecule. So one of those is the ketone, C double bond O. And one of those has to be the alkyne, triple bond C. At this point, we've used up most of our pieces. Only thing we're missing, CH3 on one side, and we have to attach this oxygen on the other side. We said we had an ester or a ketone, must be an ester. We put the CH3 next to the alkyne. There's our molecule. We could, at this point, probably put the oxygen next to the alkyne. I'm not doing that for reasons that we'll get into in 118b, which is they're not very stable. And that's a functional group where I'm saying, if you haven't seen something that looks like that, it's probably not it. But if you did that on an exam for me and you gave me that flip, I'd probably believe it. There's no real piece of information that's telling us at this level that there's some sort of difference. How we doing? So, last thing, just 30 seconds, check everything, make sure all that information you used is right. Because what tends to happen to folks a lot is you say, I know I've got an alkyne, and then you write an alkene, and you start losing points. So make sure you have everything, make sure everything stays the same. Very easy to lose points by getting excited to put that structure together and forgetting all the things we knew were true. So if you got questions on stuff, I think we're out of time, so if you got questions, come on down, we can chat a little bit. Otherwise, I'll see you guys in lectures, see you guys elsewhere, and we will have some of this stuff up on the website so you guys can take a look at.